All right, it is officially Berkeley time. Thank you all for coming to live lecture and taking out time out of your day to learn more about blockchain. Today we are going to be talking about security tokens and wallets, but before we do that, just some administrative stuff. The homework 4 was due like 10 minutes ago, but due to difficulties with the unhandled promise rejection error, and it seems like a lot of people were running into that. And I honestly had never run into that error, so I don't know exactly how to debug it. We'll give you until end of day today to submit either the correct balance of the Omkar Bank contract or code that is correct in the sense that you followed the correct steps even though it didn't result in the right output, and you'll receive credit either way. In addition, I'm aiming to release gradebook the gradebook spreadsheet by end of day today. I sent out a form late last night asking people to enter in some sort of alias that would allow them to identify their record when it's on the gradebook, because I didn't want to tie people's identity to their grades just for privacy reasons. So if you have any questions about that, just let me know. Otherwise, any other logistical questions, please drop it in the chat, or we can go ahead and get started here. Homework 5 will be out hopefully later today. I'll make a post on it, and it will be due next Thursday. All right, let's get started then. Do drop any questions in the chat. But as I mentioned before, we will be discussing security tokens and wallets when it comes to blockchain and Solidity development. I think that this is a really important topic, and as a huge security buff, I think that it's really important to understand security implications of your code and adopt defensive coding practices. So I will be teaching the first half of the lecture, and joining me is Tim, who's another member at Blockchain at Berkeley. Tim, if you want to provide a brief introduction, we can go ahead and get started.
Sure. So hi, my name is Tim. I'm currently a freshman studying EECS, and I'm also a developer at Blockchain at Berkeley. And I think I've been around the Ethereum space kind of for like quite a while now, so I kind of like understand tokens and stuff.
Awesome. Thanks, Tim. So Tim will be talking about tokens and wallets. I will be talking about security with respect to Solidity, and as well as any hacks that have occurred, or major hacks that have occurred due to poor coding practices. So let's just kind of dive in, and this is our roadmap for today. As always, I will be discussing an overview of security and the kind of motivation behind why we're giving this lecture. Then I will move towards attacks and vulnerabilities on Solidity in particular, and then defenses and mitigations. And the cool thing about this security lecture is that it's really applicable, and you may see some similarities among many languages, so you can apply the techniques you've learned into your general coding practices, and this should be familiar to most of you. So let's just kind of dive into an overview on why is public blockchain security hard. So with this decentralization, immutability, as well as transparency, you get this it's a kind of a double-edged sword when it comes to security, in the sense that anyone can call any functions that they want. They can see bugs or vulnerabilities, right? Your contract is just available to the public, and all data is transparent if you choose to make it transparent. So as a result, the public blockchain security is just really difficult. So why does this matter? Why does security matter with respect to blockchain? Immutable systems make it so that exploits are just really extremely difficult, if not impossible, to reverse the effects of. So we get the property of a blockchain as an immutable data structure. So actions are almost impossible to reverse. And thus, without a legal system in place, security is the only thing that prevents network adversaries from destroying or bankrupting your protocol and basically destroying the blockchain overall. Since there's a direct tie with the value of your product with the security of the product. If there is a hack or an exploit, you'll often find that your product loses adoption really quickly, just because these effects are often irreversible and sometimes untraceable. So let's just go through a history of some major follies in secure coding practices with respect to blockchain development. So if anyone has heard about the DAO is basically a decentralized autonomous organization. And the concept of a DAO was to create this virtual venture capital fund that is basically governed by investors of the DAO. So if you wanted, we are basically like crowdfunding different projects as token holders can submit proposals for the funding of their project and use DAO funds for that to fund their project. And these proposals will be approved by some quorum or consensus of 20% of all tokens. So basically, you're basically able to create a crowdfunding and like a VC fund just as a collection of investors in the DAO. And this protocol transfers Ether automatically to the smart contract that represents the proposal. It was extremely popular, super successful. It raised 12.7 million Ether, which is 150 million USD in June 2016, and a lot more now. But they got hacked, and so how did this hack actually occur? The creators of the DAO included in their code the ability to split a DAO in two in the case that a protocol or a proposal that that an individual has objected gets approved, in which case you want to retrieve the DAO that you had that was staked. And this would take at least 48 days before getting into an account you can control. So what happened was a coder found a loophole in this procedure where within the contract, once the split function is called, the code was written in a way to retrieve the Ether and then update the balance. While in reality, you want this flow should be flipped. You should always update the balance and then retrieve, like send or receive Ether, because what the hacker did was they recursively called a split procedure and retrieved their funds multiple times before they got to the step where the code checked the balance. So they were basically just siphoning money off this from the DAO, and they were able to retrieve 3.6 million Ether, which is approximately 150 million USD. And this is now known infamously as the recursive call exploit. So if you're interested in how the DAO works, and as well as this DAO hack is really it made headlines, and it received a lot of criticism. So be sure to read up on that if that interests you. And so another hack another loophole that was found was with regards to quick parity. So what is parity? Parity is simply an Ethereum client that provides a web interface to underlying Ethereum node software, and it provides access to basic Ether and token wallet functions, as well as it integrates seamlessly with all standard tokens. So the actual what parity is doesn't matter as much as like what the hack was. So the attacker discovered that the default function of the contract routed all calls to a wallet library, which had an unpermissioned init wallet function. So since it's an unpermissioned function, anyone can freely change wallet ownership. They can change owner rights and are able to kill it. And this resulted in the freezing of 573 wallets with a balance of more than 500K Ether, which is approximately 152 million USD back then at the time of the hack, but a lot more now. So any questions on the history? I guess this is just the purpose of these case studies is just to show you that if there exists an exploit, however small or obscure it may be, it will occur, and it will result in a lot of money being lost. So it just magnifies the need for writing secure and defensive code. So let's go to the attacks and vulnerabilities that exist within Solidity code. This is if you've taken 161 or some similar security course, this should be you should see a lot of overlap with regards to attacks on C and attacks on Solidity, just because uh, they're just features, I guess, in the language. So the first kind of over umbrella concept that we can see as a vulnerability in code is an overflow. So when we talk about different variables, they're represented by a certain number of bytes, which is 8 bits. So Solidity can handle 256-bit numbers. So in the case of a unsigned integer, you would be able to represent from 0 to 2 to 256 minus 1, which is a lot. But if you increment by 1, this would lead to an overflow. So if you go to the 256 minus 1 and then increment 1, it'll overflow and wrap around back to 0, which is the smallest available unsigned integer. And this is just behavior that you don't want, just because it are unintended behavior. So the an analogy to that is underflow. When a number is unsigned, decrementing will overflow the number. So if we take the smallest number possible, which is 0, and subtract 1, it will result in the maximum possible value, which is 2 to 256 minus 1. And so once again, like in the case of signed integers, it's even worse because you can create a you can turn it into a negative number, and if there's like a less than check, it can somehow bypass the less than check. So there are a lot of vulnerabilities or exploits that can be crafted using integer underflow and overflow. Any questions on overflow and underflow? It's pretty intuitive, but just consider that the integer just has a max and a min, and if it think of it as like a mod space, if for those of you who have some discrete math background, but if not, it's basically there is a certain range of numbers that a certain variable can take, and if you increment beyond it, it will wrap around to the start. All right, moving on. So another, I guess not a vulnerability, but just a concept in Solidity. If you are familiar with any other coding language such as Java, we have like public, private, and protected. But with regards to Solidity, we have kind of 4 types of access, access control parameters that are included with the function signature. So public functions can be called by anyone, including those inside the contract, from inherited contracts and outside users. So public is a really dangerous game because anyone can call a public function, even if they're even if the function that's calling this public function is outside the contract. External functions is similar to public functions, except it cannot be called by other functions of the contract. It can only be accessed externally by other contracts. Private functions can only be called from inside the contract. I guess that's pretty standard across all private functions. Internal functions are a bit more relaxed version of private functions. These are contracts which inherit from the parent. This is internal functions are functions in which contracts that inherit from the parent can actually use or call this function. So just kind of a good coding practice idea is to just like we coin it in security world as least privilege, or the idea of like not giving users the least amount like of access necessary to some secure system. So try to limit your access to these functions. Usually you want to you keep them private or internal unless you really need them to be public. Another type of attack that can be exploited is this is called a reentrancy attack. It's also known as a time of check to time of use vulnerability. So let's just kind of consider this scenario. I have $500 in the bank. I ask the bank to give me $500, and the bank checks, okay, I have enough money in my account. They hand me $500 and then deduct $500 from my balance. I walk away happily with $500. So is there anything wrong with this kind of sequence of steps? And is there any potential vulnerabilities that can stem from it? If you want to drop in the chat, that'd be great. Yeah, exactly. Both of you are right. So we should the order should be swapped. You should always deduct and then hand the balance because if there is a temporal difference between the actual handing of the balance and the deduction, we can basically create like a recursive call, which is similar to the DAO hack, where I can simply I can keep asking the bank to give me my $500, and before a balance is actually updated, you can if there is like a decent amount of temporal difference between the two actions, you can repeat this action like an arbitrary number of times, and you'll walk away with a lot more money than you have in your account. So this is the equivalent code in Solidity. It's pretty straightforward. You're just checking if the balance of the sender is greater than or equal to the amount, then you should return the amount and then deduct the balance. But basically, the if statement and the balances should be swapped, or the if block and then the line of code after should be swapped. Any questions on reentrancy attacks? Yeah, like as I mentioned before, it's more commonly known as time of check to time of use, where basically you should always check a condition before and make any changes you need before actually executing whatever you need to do. All right, so moving on. So let's talk about some Solidity quirks. These are just kind of aspects of Solidity that you should just have in the back of your head. And I think that there are a lot of tools that we can use to develop smart contracts securely. But let's just talk about these different quirks. So the first quirk is randomness. Everything on the EVM is deterministic. People have used now and block.block hash for business logic in a contract, but these results are predictable and can be manipulated by miners. So whenever you want to use randomness in your smart contract, you always want like a sufficient source of entropy. And unfortunately, a hash or a now time is predictable. And thus is not a significant source of entropy. So there's another concept of timestamp dependence. Block numbers and average block time can be used to actually estimate the time. So this is not future proof. So as block times can change, so make sure that if you need to achieve randomness in your smart contract, then you should make sure that you're sourcing randomness correctly. And if you don't want, and make sure that you're not incorporating unnecessary randomness into your smart contract. Another, just a bit of a quirk, I think it's very common in other languages as well. Make sure that you're locking versions of Solidity instead of saying the caret, which means any version of Solidity above version 0.5.0. You should just lock it such that you're in the case that a new version comes out that hasn't been tested against your smart contract, it's not introducing any new vulnerabilities that you haven't checked. Pretty straightforward. This is mainly for your reference. There are a bunch of tools to help to introduce semantic checking of code, static analysis, runtime analysis, decompilers are very common. tools that exist throughout all of programming and are simply used to um, check uh, check any like code vulnerabilities as well as runtime vulnerabilities using these tools, and they're really helpful in terms of finding code and code vulnerabilities. And it's good that these tools extend to smart contract development. Next, don't forget open source libraries. We have Open Zeppelin, which is a library that is available and is open source for writing secure smart contracts on Ethereum. You have a bunch of features that you can use using Open Zeppelin in terms of developing your smart contract. Like you can, it provides ownership, safe math, push and pull, and then integration with standard and basic tokens. So do check out Open Zeppelin whenever you're writing a smart contract. Next, we're going to talk about mitigations and defenses. This is it's a lot of bullets, but I think like the TLDR is don't just keep it simple. Don't go too crazy writing code, and I think that concise code is a really important skill, or the ability to write concise code is a really important skill for any software developer. And don't try to implement crazy logic if it may introduce some vulnerabilities or loopholes. You should use audited and tested code. There are many ways to do this using test-driven development, or just writing many unit tests, fuzz testing. Testing, it's really important to test your code, even though it's like boring, and most of the time we like write tests in school to pass an auto grader, as opposed to like making sure that our code is extremely robust. But that's beside the point. But you should prepare for failure. I think like ensuring that you have defensive coding practices is really important. That if there is a vulnerability that you can find, or even if you can't find it, then and you should assume that an attacker will exploit it, and they will, especially if this could result in like high economic gain for the adversary. And yeah, keep these quirks in mind, and also these vulnerabilities and features that we've been discussing. So yeah, these are just, I'm just gonna like rapid fire a bunch of takeaways that you can that seem intuitive, but it's really important to keep it in mind. So yeah, avoid external calls when possible, and for that matter, like avoid public calls as well. An external call is a call from one contract to another untrusted contractor account. So the DAO hack and parity multi-sig hack were stemming from external calls. So just try to avoid external calls unless like absolutely necessary. Pull is greater than push. So pushing is the idea of is the logic of a contract transferring immediately to an address after the logic is complete. So the contract is like taking the aggressive approach of executing a transfer, but it's vulnerable if the recipient contract is poisoned. On the other end, in the case that the recipient contract is poisoned, you can never retrieve whatever currency or data that's being sent to that contract, or you can't like revoke it. On the other hand, pulling is a way better logic, and it's lazy. It gives addresses the ability to get their data or their money, kind of like a withdraw function. So you should just use pulls instead of pushes. Asserts and require. I'm sure you all have encountered assert statements and assert conditions. So require is used for input validation. It should be done on any user input. So like requiring that an input string is alphanumeric and less than or equal to 20 characters, as I attempted to do but failed in my Google form. It should be done just to ensure that you're not getting any like any input that you wouldn't expect. And both asserts and requires will throw if the condition is false. So you're able to protect your code in that regard. The sort condition should only be used for internal states or to check if a contract has reached an invalid state. And by following this paradigm, it would become possible to use a formal analysis tool that can actually ensure that your requires and asserts will ensure that an invalid opcode cannot be reached. Another quirk, I guess like it's very similar to Python. Don't integer division rounds down. So make sure if you need some more precision, like store some sort of multiplier or store both the numerator and denominator. Also, all data is public, so make sure that you keep. Many applications will require data to be private until some point. So make sure that you're not like having your users publish information too early. So in the case of rock, paper, scissors, let's consider that if both players have to kind of submit their move, but we have to ensure that there is, first of all, that it's binding. So each player is like bound to a move before they know the other player's move, and each player is able to hide their move from the adversary. So ways we can do that is you can submit the move or submit the hash. I think submitting the hash is probably the best, just because it provides both binding and hiding properties. And so what you would do is you submit the hash and then to some oracle or some contract in this case, and then both players will submit their moves. And then if the move is not matching the hash, then you should throw it out. In which case the player kind of just backtracked and changed their move. And then a final takeaway, I guess, is beware of the possibility that some participants like may not be available all the time. And in this case, like you should have some time limit or an economic incentive to make sure that participants are submitting their information in a timely manner. Otherwise, a malicious player can basically like hold out another player by just not submitting their move, and this would lock the funds in the smart contract without being transferred to the appropriate user. Yeah, I think like you can't really emphasize this as enough. Just make sure you're always testing and try to get 100% coverage. Fuzz testing is the use of random outputs and just like a bunch of random outputs, and it's been pretty successful. Test-driven development, unit testing is always a must, and you should be running it every time you're compiling and running your or anytime you push code. So now I am going to hand it off to Tim. I'm going to stop my sharing. If you do have any questions, please drop it in the chat and I'll be more than happy to answer it. But yeah, now Tim will be talking about tokens and wallets.
Cool. So let's talk about tokens. Sorry, give me 1 sec to share screen. Then, okay. Let's present, and then, cool. So, so first, I would just like to clarify a couple of kind of misconceptions about tokens. So, tokens are not the same things as currency, and you actually don't need to create a blockchain to build a token. Tokens are actually like this concept of kind of like a way to like store value, and although you don't need a blockchain to store a token, the blockchain does provide like some advantages for storing tokens, which we will get to later. So. Also, there's a difference between tokens and coins that are native to the networks. So for example, for the Bitcoin network, we have things like Bitcoin. And for the Ethereum network, we have like Ether, which is kind of like the currency that the network runs on. And although like these currencies like act really similarly to this kind of token that we'll talk about later, there are still some differences in that this is like natively supported by the chain and doesn't like explicitly implement all the methods. So I guess like what a token is that it's simply an entity with some sort of value associated with it. And we'll get into like what sort of value these tokens have and like the 2 main types of values. But fundamentally, a token is just something that stores some kind of value. And And you might have like heard about something called an initial coin offering, where like a crypto company is kind of like selling off a lot of their tokens. So basically, what is happening in an ICO, just to clarify, is that the company is selling out tokens, and these tokens represent like shares of the stock of the company. So kind of like instead of like selling shares like on the stock market, a lot of crypto companies prefer to sell their shares using tokens. And and finally, the beauty of tokens is that they can be very easily built, and they're also super flexible, and they have very standard smart contract logic behind them. So all tokens can functionally do the same things. And this allows for a lot of cool things like interoperability, where like one contract can interact with many different tokens without even knowing the underlying implementation of the token. All right. So when building a token, the most important distinction is to like know the true purpose of a token and why it can be great to build them. There are a lot of like really great token applications out there, but there are also a lot of applications that aren't so great. So yeah, tokens can act as symbols or values for smart contracts or dApps, and a lot of tokens are really important in the logic of these applications. So for example, a token would be something like a USD coin, USDC. This is a ERC20 token. We'll get into what is this later, but as you might imagine, that's quite important for like the smart contract in general. So just very briefly, let's talk about the cycle of tokens. So the first step when you make a token is that you need to create the token. This is usually done by minting. We'll get into like how exactly to do this later, but basically somebody needs to instantiate the token. And then next, the token can be purchased by a customer or a user, and then that token can also be transacted and traded with other tokens. Okay. All right, so our first category of tokens are fungible tokens. So, so what makes a token fungible is that one token is functionally indistinguishable from another token. So I guess like first to kind of like clarify, we will be building tokens on the Ethereum platform, and there are some like token standards that have been set by the Ethereum community. So the standard for the fungible token is called ERC20, and we'll get into and what the standard looks like and like why they kind of made the standard later. But basically the purpose of standardization was to kind of like create this framework for creating an ERC20 token so that like all ERC20 tokens have similar behaviors and they can like be used in smart contracts interchangeably. And and why we call these tokens fungible is that one token will always be worth the same as another token. For example, when we look at our USDC example earlier, like if I had a USDC and someone else had a USDC, right? My USDC is like not the same. Well, actually, sorry. So my USDC would be functionally identical to the other person's USDC, right? We can like trade it, although like nothing would happen, and like mine's not worth more than theirs or anything. And yeah, if you want a useful analogy, you can like honestly think of things like dollars, right? Right, like you can treat like money as dollars as like functionally identical to one another, and the only thing that really matters is like how much of it you have. Okay, and yeah, all that is necessary to build an ERC20 token is to implement the ERC20 interface, which cool. So this is kind of just an outline of the interface. As you can see, there are a couple of really important functions. So for example, here we have a total supply. So this basically just like returns how many tokens there are in circulation. And then next we have balance of, which finds like how many tokens a specific user owns. And then now we have transfer, which basically transfers some amount of tokens from like the initial pool of tokens to the user. And then we have transfer from. So a lot of people get confused on the distinction between a transfer and transfer from. So the distinction here is that transfer is intended to be used when is to be used by you to like get tokens for yourself, or when like your account has been authorized by somebody else to take control of their tokens. And we'll get into like how this is done later. Whereas a transfer from is usually a more generic function. It's the safer function because right, you have like the from and the to, and then like a lot of the same checks run through, but transfer from is just generally a more safer alternative to transfer. All right, and then next we have our approve function, and this basically this basically allows a certain user to transfer some amount of funds from another user's account. So this kind of goes back to like what we discussed in security earlier, where we need to kind of like compartmentalize like who has access to which portions of the contract to make sure that like someone isn't trying to spend someone else's tokens. Okay, I have a lot of coins. Okay. Yeah, and then we have allowances. Allowances, once again, this is another form of access control. It basically allows a certain spender to spend like some amount of a certain owner's tokens through functions like transfer or transfer from. And then finally, we have the two events, transfer and approval. And these events, you probably covered these in Solidity already, but they basically alert like standard infrastructure, such as like servers and stuff, when things get done on the smart contract. All right, so yeah, this is just kind of like a more detailed description of like the actual interface with some comments and yeah, basically what we kind of like talked about what each of these functions did before. Okay, so there are also some necessary fragments that you have to implement in your contract before you can do the ERC20. And although like these are not like necessary, like you don't have to implement the data structures in this way, it is highly recommended that you do. So functionally, we kind of need two things, right? So the first thing is that we need to keep track of the balances for each account, right? We need to like keep track of like how many tokens that each person owns so that like we can edit it and actually like show like who owns which tokens. And the way we usually do this is a mapping between the user's address and their uint in terms of the balance. And then the second thing we need to store is basically a mapping between approved accounts and between like kind of like accounts and who is approved to spend a token from them and how much tokens they are allowed to spend. So so we usually do this using like a nested mapping. I know it looks kind of confusing, so we can kind of like break it down. So the first mapping is that we map an address to something, right? Some mapping, right? And this address would be the owner of the account. So now that we know that this address is the owner, the account owner, now we basically have like a mapping for each account owner. And inside this mapping for each account owner, we have every person that is approved to spend some amount of tokens, and then the amount of tokens that they are allowed to spend. So in this way, we can kind of like keep track of the different like approvals, and we can like also like delegate certain people to like spend other contracts. And once again, you do not have to write these mappings in this way. This is just like what is highly recommended by the Ethereum community and what would make it most easy to kind of like implement a smart contract. Okay. And then on top of that, we need to like store some amount of information to basically tell other people what our token is doing. So the three most important things here are the name. So what is your token called? Your symbol. This is usually like pretty short and all caps. And the purpose of the symbol is that if your token gets listed on some sort of like DEX, like Coinbase or Uniswap, there's like a very clear way to like reference what your token is without spelling out the entire name. And then finally, we have decimals. So this is basically to how far down like your token can be split. Usually the standard is 18. If you're building your own tokens, you probably don't need to worry about changing it from 18. But what this 18 basically means is that your token can be split down to 18 decimal points. So or like the smallest denomination possible is 10 to the 18, 10 to the negative 18th. You have a chat? Okay. And yeah, and the reason that it's 18 is that the smallest amount of ether, is a way, and one way is exactly 10 to the negative 18th of one ether. So kind of like flows well with how like the Ethereum blockchain is already configured. All right, so let's talk about token tools for a sec. So even with all the functions outlined in the interfaces, building a token can often be really difficult. So we have some resources to actually make it even easier to create these tokens. The most notable of these resources is OpenZeppelin. So what OpenZeppelin does is that it's a company, and they have like lots of different like smart contracts that are audited that you can extend. And specifically, OpenZeppelin actually has an implementation of a ERC20 token. So like all the functions are filled out for you. The only thing that you need to do is to implement what OpenZeppelin has done and pass in your custom variables, which will probably be like your name, the symbol, and all that stuff. And then that way you can get started with a ERC20 token really quickly. So this is like something really nice if you guys like want to build tokens in the future. All right, so now let's talk about the next category of tokens, which are non-fungible tokens. So the important difference between a fungible token and a non-fungible token is that each non-fungible token is unique, and non-fungible tokens do not have the same value in between them. So for example, some tokens might be worth more than others. And so yeah, the best example here would probably be CryptoKitties. I'm sure you guys have all heard of CryptoKitties, but what they did is that they had a bunch of cats, and then they associated each cat with a non-fungible token, so that when you bought a token, you could be sure that your cat was unique, and there was no other person who owned the same cat, because there is no other person who owned the same token. Because once again, there is only one possible there is only like one single instance of that non-fungible token. So a useful analogy for this would be to think of like non-fungible tokens as like really old collectible things, like for example, baseball cards, right? So like although like all baseball cards fall under like one general category, and you can like describe them with one data structure, each baseball card is unique, and there's only one of each baseball card, and the baseball cards can be worth different values, just like non-fungible tokens. So the standard here is called ERC 721. This is what the community has mostly agreed to. And once again, implementing ERC 721 tokens is pretty similar to implementing the fungible tokens. And it's just like an interface that we will talk about shortly. All right, so yeah, once again, here we have some examples of non-fungible tokens and like some different metaphors. So you have like collectibles, Pokemon cards, and then deeds as well. All right, so this is kind of like a contract that would implement an ERC 721 token. So as you can see, there's a lot of similarity between the 721s and the ERC 20s. So right, once again, we have name, symbol, total supply, how many tokens have been minted, and balance of basically returns how many tokens that each owner, that like each person owns. All right, and then we have some functions that basically define ownership. So first we have owner of, and this basically returns, takes the token ID and returns who owns the owner. And then next we have approve. So this would basically approve a transfer to a certain address for a certain token ID. So usually this would be called by the person who owns the token, and there's actually like checks to make sure that it is called by the person who owns the token. But this would basically be like someone saying like, okay, I'm going to give my token to someone else, and I want you to know, so that when that person comes looking for my token, the contract can actually give that person my token. All right, and then take ownership would be the analog to approve. Basically, if somebody gave you a token, then take ownership is what you would use to get that token. Okay, we have a question. What does token minting entail? Okay, so token minting is basically the process where you create a token. So like specifically in the case of like non-fungible tokens, I'm not sure if there's a slide in here, but like we can kind of talk about how like each token is actually represented like by the struct, and in like the most low level implementation, minting a token would basically be to like create a struct and assigning that struct a token ID, and then storing that token in a data structure that we will get to later. But yeah, that would basically be like what it takes to like mint tokens. So yeah, I hope that kind of cleared things up. All right, and then once again, we have the standard transfer function where someone can like give someone else a token and with the token ID. And then finally, we have a token owner by index. So basically this takes So yeah. So basically, what this does is that it takes the owner and it like returns the token and it returns the tokens and then it, sorry, distractions, but yeah, it would basically like return the tokens that the owner owns. And then we also have a couple of metadata functions here where yeah, basically it returns something called a info URL. This is kind of like a standardized way for like a DEX to display like more detailed information about the token. And we can like link some slides if you're interested. And and lastly, we have some events. So these events are pretty similar to the events for an ERC20, basically notifying other people once a transfer is done and once an approval is done. And before we move on, I just wanted to clarify one thing, and that is the concept of a token ID. So when we talked about fungible tokens, right, each token was the same. So there was no need to assign a unique identifier to each token. However, when it comes to non-fungible tokens, each token is different, which means that each token needs a unique identifier. And that is basically how like we tell these tokens apart and how we basically keep track of tokens when we want to transfer them. All right, so I guess like before we move on to wallets, does anyone have any questions about tokens? All right, then so let's talk about wallets for a bit. So basically, what is the wallet and like why do we need a wallet? So fundamentally, a wallet is a way for users to manage their tokens or cryptocurrencies. Uh, I would say 99% of wallets have user interfaces to make it very, very easy for users to interact with their tokens and their cryptocurrencies. And in more detail, each wallet needs to perform, I would say, 4 key functions. So first, it needs to allow user to control access to a user's tokens. So for example, you own some tokens and someone needed to, and like you wanted to like do something with those tokens, like transfer them. What is take ownership for? I'm not sure what you mean by take ownership. Do you want to like elaborate a bit on that?
I think it was the previous slide. Sorry, so I asked the question a bit late. It is because if there was a function, I guess, take ownership. Can you go back one slide? Take ownership. That guy, yeah.
Yeah, definitely. So the way that take ownership works is that oftentimes we would have like approvals, right? So let's say that like I'm trying to like give my token to someone. So I could approve them to take the token right here, and then it will be stored in the smart contract. And then take ownership would basically be the person the person who I wanted to give the token to. They would call this function, and then the smart contract would give them that token. Yeah. The reason we kind of like split it up into approve and take ownership is from like the security concerns. This is like the difference between like pushing and pulling, which was covered earlier. Where basically like instead of directly giving the person the token, we make the person ask for the token.
Thank you. Got it.
All right. All right, so yeah, back to 4 main uses of a wallet. So secondly, a wallet needs to allow a user to manage keys and addresses, right? Often in the crypto space, it's a good security practice to use like multiple different addresses to kind of like mask what you're doing. And a wallet would need to be able to allow you to make different keys and addresses. Right. Third, a wallet needs to be able to track the balance of everything that you own, right? Similar to like a real world wallet. And finally, a wallet needs to be able to create and sign transactions with your private key because like when you send a transaction to the chain, it needs to have your private key on it, or it needs to be signed by the private key. Otherwise, the chain doesn't know that it actually came from you. Okay, so I guess the formal definition of a wallet is that it's simply a data structure that stores and manages a user's public and private keys. So how this works is that the private key is basically a key that is stored on the wallet and never leaves out of the wallet. But there's a function that the private key can do called signing a transaction, which basically verifies that it came from you. And this is basically how money is sent, so that people make sure that like you are the one actually sending the money. right? And now the public key allows receiving money to the wallet. The main purpose of a public key is to kind of like identify who you are. So basically, if someone has like sent you some money, the contract needs to be sure that like you're not an imposter, and they use like the public key to basically to make sure, yeah, for security concerns. Right. And yeah, once again, if you make a transaction to the blockchain and it's viewable using your public key, so it's kind of like an identifier for like who you are in the crypto space. All right, so now let's talk about some different types of wallets that are out there. So first we have our non-deterministic wallets. So basically how this works is that there is a collection of independently randomly generated keys, right? And then in each of these keys, there is a public key and a private key, which is sufficient for creating an account. Now, there are some disadvantages to this, mainly that it's cumbersome to maintain, backup, and import because none of these keys relate to one another, right? So they all need to be backed up manually, and they all need to be backed up. Otherwise they will be lost. And once again, the reason that oftentimes you need a lot of different addresses is to like reduce is to like kind of like improve privacy, because oftentimes if you reuse the same address, it's very traceable throughout the blockchain because all your transactions have your address on it. So oftentimes people make multiple addresses to kind of like mask their identity. All right, so in contrast to non-deterministic wallets, we have something called deterministic wallets, where oftentimes you have this like one seed, right? And the seed is really, really important because what the seed does is that you can generate a lot of different keys from this one seed. And the advantage of this is that once you have the seed, you can derive all of the keys. So when you're backing up the wallet, you only really need to back up the seed. Right? The disadvantage is that if you lose the seed or if somebody steals the seed, then that person will have access to all of your accounts. So it is really, really important not to let the seed fall into the wrong hands. However, this is often easier done than through like a private key because the seed is often stored on your machine and you don't really interact with the seed that often. Whereas every time you sign an account, you are interacting with your private key. All right. So another type of deterministic wallet is a HD wallet, and if you've ever used something called Truffle HD wallet when you're doing a smart contract deployment, um, that is basically an HD wallet. So basically, what an HD wallet is that it's a collection of keys derived in a tree structure. So here we have this like one seed, right? And from this one seed, we create one key. And then from this master key, we can create a different child keys. And from each child key, we can create still more keys and so on and so forth. And the advantage of making keys hierarchically is that you can have something called structural management. And this is basically where you like give one person one branch of the keys to like use. But if that person turns malicious, they do not have access to the rest of your keys, right? They are still stuck on their one branch, right? So yeah, says your users can create a sequence of public keys without having access to the corresponding private keys. And so this is like really, really useful for things like access control, right? Once again, you need to keep the key private. If the seed gets out, then the entire wallet is compromised. Okay, and now let's talk about multi-signature wallets for a second. So far, the wallets that we've covered are only for single person use, right? It's one person using a bunch of accounts for a wallet. Right? Yeah, only one account creates an empty wallet. However, using a multi-signature wallet, you can have several different accounts use the wallet where one of them will be the creator. And this is very, very similar to things like secret sharing schemes in classes like CS70, where you have like a bunch of people, let's say like n people having access to the wallet, right? And you only want something to be executed once you have like a certain amount of that n people agreeing. So here are the basics of what a multi-signature wallet needs. So first we need a list of people who are allowed to do things. These are your end people who basically have access to the wallet. And you also need a bunch of rules and these rules basically govern like how many of these people need to agree to something before it happens, right? For example, a very common wallet is a 2 out of 3 wallet where 3 people have access to the wallet, but and 2 of them need to agree before the wallet does a transaction, right? Another type of wallet is like 3 out of 5 wallets, which kind of like follow the same principles. right? On top of that, we kind of need our wallet basics. So basically the same things in a individual wallet. So yeah, a way to receive Ether and like a way to like do transactions on the chain. So like submitting requests, stuff like that, and a way to agree to a request and submit the request. And finally, a way to resubmit the request if the request fails. And yeah, and these four things basically allow like people, a group of people to basically share the wallet without like one person maliciously taking control of it by themselves. Okay, so yeah, here are some common use cases for a multi-signature wallet. So the first use case is that you own some Ether and you want to store it securely, but you're concerned that you might lose your private key or it might get out. So what you do is that you can create a 2 out of 3 wallet so that even if one of your private keys get like it's leaked and is compromised, you still have 2 of the keys, which means that you still have a majority control over the wallet. And oftentimes a lot of people store these keys in like really disparate locations. So like one of them might be on like a hard drive, another one might be like backed up on like some mountain in Switzerland, so that like it's impossible to like lose all 3 keys and lose access to your crypto that way. Right, and the second use case for a multi-signature account is when you like actually want to share your wallet with somebody else. So let's say that like you have a wallet that is jointly owned by 2 people. So you have one private key and the other person has the other private key. And what you can do is that you can do a 2 out of 3 system by having like the third private key like somewhere where like no one can access it, so that like the only way for a wallet transaction to go through is if you both agree on what to do with the wallet. All right, so I believe that concludes my part of the lecture as well. This is the attendance link. I can probably paste it in the chat as
Oh
well.
no,
This
for
recruitment forum.
this, that's a remnant of past I guess like a past offering. We take attendance just like by looking at the Zoom logs. So don't worry
Okay,
about that.
okay,
Yeah.
I see, and that's fine. Yeah, scratch that.
Cool.
And
Thanks.
cool.
Yeah, thanks so much, Tim, for your time. We'll stick around for a few minutes regarding questions. I am in like literally 5 minutes. I'm gonna make a announcement with regards to the homework 5, which is just released on the GitHub. It's super chill. There's a short Solidity like security quiz that will be graded on completion. So just fill it out, and then like a small assignment with regards to um, adding like ERC tokens to your MetaMask wallet. So that would be pretty cool. So I'll send that out, and I also was able to get a public spreadsheet for the grades with your guys' alias. So as you add the alias to or submit your alias to the Google form, I'll include that so you can actually like view your grades. And if you have any concerns, of course I'm not perfect, so please do make a private Piazza post and we can figure that out. I just want to make sure that you all are getting credit for stuff that you've done.
Yeah, definitely. And yeah, I just want to say like thank you so much for having me. It was really fun getting to like talk about tokens and wallets with all you guys. And yeah, if you have any questions, feel free to ask. We'll stick around for a bit.
Yeah, thanks, Tim.
Yeah, I guess I had a quick question on like minting.
Mhm.